Hello. Welcome to Introduction to Terahertz Technology and Applications with Peter Siegel. I'm Douglas McCormick, your host for this IEEE Microwave Theory and Technique Society webcast, which is sponsored by National Instruments. Before we start, I'll mention a few housekeeping items. First, this presentation will be archived. A recording should be posted about 24 hours after we close, and all registrants will get an email when it goes up so that you can revisit it or share it with colleagues. Second, we do encourage questions. We'll answer them after the talk, but you can submit them at any time during the discussion. Please enter them in the Q&A box on the left side of the conference window and hit submit. Third, a quick word about the interface. You can enlarge slides by clicking on the green rectangle at the top right of the slide area. If you inadvertently minimize the slide area, slides, you can bring them back by clicking on the slide icon at the bottom of your screen. If you're listening over your computer speakers, you can adjust the volume in the media player area at the upper left of the screen. And please remember, you may also need to adjust your system's master volume. The icons at the bottom of the conference window include a green file folder. This links to a resource page from which you can download a PDF copy of today's slides. It's now my pleasure to introduce our speaker. Peter H. Siegel is a researcher and consultant who focuses on terahertz, microwave, and infrared end of the spectrum. He holds appointments in the electrical engineering and biology departments at the California Institute of Technology and at NASA's Jet Propulsion Laboratory. He is also founder and CEO of THC Global, an international collaborative research consulting team working on a wide variety of THC research and applications. Dr. Siegel has been working in the area of millimeter and submillimeter wave technology for more than 70 years, serving as PI and co-investigator on more than 75 R&D programs, including some delivering critical hardware to major spaceflight instruments. He has more than 300 published articles, and among his other activities, Dr. Siegel is General Secretary of the International Society for Infrared, Millimeter, and Terahertz Waves, founding editor of IEEE Transactions on Terahertz Science and Technology, and a leader of MTT Committee 4 on THC Technology. Dr. Siegel received his bachelor's degree in astronomy from Colgate University and his master's in physics and PhD in electrical engineering from Columbia. And with that, it's my great pleasure to turn the virtual podium over to Peter Siegel for Introduction to Terahertz Technology and Applications. Peter?
Thank you, Doug. It's a great pleasure to be here. I hope everybody listening can join with me in having a nice time talking about terahertz, a subject that's of great interest to me. Let me just correct one small thing that Doug said. It's not been 70 years since I've been in the field, so don't get the wrong idea. I'm not 95. I've only been working in the field about 40 years. So I'll try to give you as much of that experience as I can in the short time that we have, and we'll see if we can't get everybody up to speed on essentially what terahertz is, how it's used, and give you a few caveats about how we go forward in the future in this field. So what I'd like to do is get right into it and begin with a just overview of the discussion topics I'd like to try to cover. And before I even begin, we have to set some ground rules here, because terahertz these days is quite as much a buzzword as it is an interesting field of study. And so people tend to stretch the boundaries to suit the research that they're working on, because it does help when you're working in a field that has a well-known buzz term like terahertz. So for purposes of this discussion anyway, we're going to confine terahertz to be the frequency range from 300 to 3,000 gigahertz. That's 1 millimeter to about 100 microns in wavelength, corresponds to an energy, a KT energy of about 1 to 12 millielectron volts, and an equivalent temperature between about 14 and 140 Kelvin. Note that's below the 300 Kelvin background that we're used to on the Earth. And the millielectron volt is important because we're going to be talking about molecular interactions and not atomic transitions, which are more familiar to most people in the optical and near-infrared regions. So we're going to start with just a few words about the advantages and some of the constraints that terahertz technology has associated with it. And then I want to switch over to some of the traditional science applications that gave rise to the field in the 1970s. And then we will talk a little about the approaches that people use in the field to generate and detect terahertz, and then how those approaches are put into commercial use. And of course, one of the most interesting applications these days, and one that is touted very often, is terahertz imaging. And we're going to talk a lot about whether that's useful or not and what you can really see in the terahertz regime that differs from what you get in infrared optics and microwaves. And then I want to finish off by just looking quickly at some of the RF effects that terahertz has in bio world, and we'll talk a little about some applications and some future potential work that people are focusing on now to bring in, of course, the new revolution in bio into this traditional electrical engineering and physics field. And I'll conclude, and then we'll have time for questions. And at the very end, I won't spend any time on the slides. I've just put in a bunch of slides that have the references that I am going to use for the various topics I'll bring up here. And I've also put down some of the major conferences that focus on terahertz and a couple of journals that have come along in more recent times that focus on the terahertz field. So there's a lot to talk about, and we'll see how far I can get in this short 45-minute period, and we'll cover a whole bunch of different things as we go through this. So first, let me get to the constraints and advantages of terahertz. So we'll start with some of the things that people have touted as reasons they like going into this field, either moving in from the microwave up in frequency or down from the infrared into this regime. Remember, terahertz is sandwiched between the far infrared, which is sort of 100 microns and shorter in wavelength, and the microwave regime, or the millimeter wave regime. When I was a student, we didn't really call it terahertz. We called it submillimeter, which of course is a more traditional way of labeling the frequency bands above microwave. Millimeter, of course, is the band that is the most utilized and the most familiar to people in the microwave world, going from about 30 gigahertz to 300 gigahertz, and then submillimeter as we approach wavelengths shorter than 1 millimeter, and then we would call it far infrared once we got above 100 microns. So really, submillimeter is a term that is more traditionally applied to this wavelength range. So the thing about submillimeter is that it has a very strong interaction with matter, all states, liquid, gas, and solid. And that strong interaction means that you're going to have some interesting spectral effects, and you're going to be able to have some contrast when you deal with dielectrics and metals. And so the mechanisms and those interactions are so strong that, in fact, they really drive and define the terahertz region. And we'll talk about that when we start getting involved with bio applications later on in the discussion. There are certain materials that are transparent in this frequency range, mainly some plastics, some ceramics, and a few dielectric crystals that mean you can see through these materials in this particular frequency range much better than you can in the infrared or optical. There are naturally occurring spectral signatures which have to do with molecular motion, and these are mostly apparent when you have lightweight gases under low pressure. We'll talk about that soon. But you also get some spectral signatures with liquids and solids that are much broader, or gases at atmospheric pressure that are much broader, that occur only in this frequency regime. And again, that makes it a unique spectral band for identifying certain material properties or certain gases that exist in nature, and that's one of the things that people started working in the terahertz frequency range to detect and measure. It's a natural frequency for femtosecond probing, so if you have very fast reactions and you want to be able to track those reactions and where molecules move, for example, or where charges, a charge motion in structures, you can use terahertz for that very nicely to actually measure how things move at the femtosecond scale. It's got very high sensitivity for traditional signal detection because you can use techniques that come out of the microwave regime. So if you're familiar with heterodyne or radio frequency detection techniques, you'll know that you can get very high signal-to-noise, back to over 100 dB of dynamic range in some cases, and those same techniques apply in the terahertz band. So you can have extremely good sensitivity with very wide dynamic range for your detectors. There are aperture advantages if you compare directly to millimeter wavelengths. You just scale the frequency up for the same antenna diameter, and you can scale the resolution or the pixel size down linearly with aperture diameter, and that gives you a real portability advantage in some applications if everything else is constant. There really is no effect from terahertz radiation that anybody has come across other than heating, and we'll talk a little bit about that at the end of the talk, but you can pretty much say for all practical purposes that terahertz is non-ionizing radiation, so compared to X-rays, for example, we don't have to worry about terahertz affecting any kind of atomic structure or doing any kind of damage to genetic material when you're exposed to it. The optical tolerances are quite a bit lower than you find in the near IR or the optical regime, so our antennas don't have to be quite as well surfaced, even though they might be large, and you don't have to worry as much about pointing as you do at much shorter wavelengths, so that's an advantage. And there's huge bandwidth available. If you just think about the frequency regime from 300 to 3,000 gigahertz, there's practically no signal bands in that range that have been assigned at this point in time. And so if you're interested in having wide dynamic signal range, this is a frequency band that you can go into without worrying about interference, except for radio astronomy, which we'll talk about later too. And of course, because all of these things are new and not so well explored, there may be some untapped potential in this frequency range that makes it quite advantageous. But let's talk about some of the constraints, because there are many of them and they limit the applications quite severely. So the first thing is that in this wavelength range, the material losses, no matter what you're dealing with, whether it's a plastic or whether it's a crystalline material or quartz, something of that sort, the losses, the dielectric losses, are very, very high compared to what you get in the optical regime. There is no such thing as the equivalent of optical fiber in the terahertz range because of the interaction with phonon modes in dielectrics and because of the high ohmic losses in metals. So you can't propagate terahertz energy in any material without suffering significant loss, whether that be a metal waveguide or whether it's a quartz substrate or a polyethylene substrate, which has low loss but not very, very low loss compared to other frequency regimes. So that's a very big limitation. And in fact, even in the atmosphere, the water and oxygen absorb very heavily, and so you can't transmit distances of more than, you can say, maybe a kilometer, maybe a couple of kilometers at the low end of the terahertz band, and we talk about meters or tens of meters at the high end of the terahertz band before you've absorbed very, very significant amounts of power just in the atmosphere itself. The other thing to think about, as I mentioned briefly at the beginning, is the background limited detection sensitivity. Because we're sitting here on the Earth and it's 300 Kelvin background temperature, and we were talking about signal levels that are in the tens to 100 Kelvin range, we are almost always swamped by the noise background around us. Unless we do something like band limit our signals so that we can reduce the noise background, it's very difficult to detect any coherent terahertz signals at room temperature or in this environment where we have normal pressure, atmospheric pressure. I mentioned that we can do spectroscopy, but it turns out that at the atmospheric pressure environment we're in, the normally very narrow band molecular signatures that people are looking at get pressure brought into quite wide bandwidths out in the gigahertz range, where the natural resonance might be a megahertz or two. And so that hurts when you're trying to identify particular gases in high pressure environment. Or in liquids and solids, it's even worse. The typical spectral signatures in this band tend to be several gigahertz to tens of gigahertz wide. And so picking them out in the background of several different spectral sources is quite a challenge. And we'll look at some examples of that as we go through the talk. The other thing that comes into play here with imaging especially is there's very poor contrast, both because the thermal differences in the environment that you're trying to measure, if it's a passive sensor, or even the differences that you get with an active sensor, really suffer from speckle and very large reflections off objects that would normally have a very minimal contrast in the passive environment. If you're doing active work, you can get quite a big reflection off things, even like paper and cardboard, for example, that will swamp your background signal. So you have to be careful how you do imaging in this wavelength range. And again, we'll talk about that. And again, a lot of people talk about terahertz being used for very high-resolution imaging, and you have to remember that when you're working with a wavelength scale of about 1 millimeter, that your focused spot size is going to be also of the scale of 1 millimeter, and so you can't really do very high resolution imaging in this range. And if you do attempt to do so and your focal length is long, then you're going to have a very, very large aperture. So these apertures are much, much bigger than you might think about if you just imagine trying to imitate an optical system in the terahertz band. You're talking about diameters of 1,000 times or more what you need for a lens or mirror in the optical regime when you want to get similar type of spot size here in the millimeter. And then, as I already mentioned, there's serious losses, but there's also dispersion. So even propagating a pulse is quite difficult in this range. And maybe the biggest hurdle up to date has been the very high cost for components and instruments. So I hope I didn't discourage you with so many disadvantages, but we're going to talk about some of those as we go through this and see where they come to play. So before I get to that, let's just sort of talk a little bit about where terahertz comes from and why it's so important an application for science, and the investment in this frequency regime has been quite significant, as you'll see, and the reasons behind it really come from basically 4 areas in historic development. The first being astrophysics, and this is something that comes about because the particular signatures that we can detect in this wavelength range that are unique have to do with molecular motion, especially in regions that are cold and low pressure, as you find outside of stars or in the center of galaxies, in outer space in general. And because we can measure unique vibrational motion or rotational motion from molecules that exist in the interstellar medium and intergalactic space with terahertz receivers and fingerprint these molecules exactly, this has been a very strong driver for a lot of people interested in cosmology and evolution and structure of the universe. And I'll show you several examples of that as we go through. Also, people who were doing plasma work in the early days were using terahertz for measuring electron cyclotron resonance parameters and temperatures of hot gases in fusion reaction systems in tokamaks, and they sort of brought a lot of technology into this field back in the 70s and 80s, maybe a little less so these days, but nonetheless contributed a lot of research and technology into the field when it first started. There were always several non-destructive evaluation techniques that use terahertz for their very high sensitivity to water content, for example, or the ability to see through certain materials, but they're very niche applications, and I'm not going to talk too much about them, but I think the most interesting I've heard about was a technique for measuring the raisin content in raisin bran on an assembly line process as the boxes pass through a transmitter that could distinguish between the dry flakes and the damp raisins and count the numbers in the box. But things of that sort pop up every now and again, and although the technology is expensive, if you have an application that really needs this kind of NDE type system, then terahertz can be quite useful. And then in quantum physics and spectroscopy, this has always been a field that has been very useful for understanding quantum physics and behavior of molecules in small groups and under low pressure. So that's always been a strong science driver. And then finally, most recently, with the advent of time domain spectroscopy, which we'll talk a little about, there's been a lot of interest in ultrafast chemistry and now nonlinear optoelectronics. And I'll mention communications and imaging. Those are the two things that I think people have been talking about most as potential applications for terahertz. But before I do, let's talk a little about space science and give you an idea of where terahertz fits in and why people are so interested in this regime for those applications. And I want to just mention the group of people that I worked with for more than 25 years at JPL, who really contributed to all the things I'll be talking about here. And they're just shown on this slide, all the folks who were in the group that we started at JPL in the late 1980s. All right, so let's talk about astrophysics a bit. So the terahertz regime, as you can see from this chart, which shows basically the full electromagnetic spectrum from long wavelength meter scale radiation all the way out to the UV, this gives you an idea of why terahertz is of interest to space scientists and less so to everybody else. It's a chart that shows attenuation versus wavelength if you were looking straight up and trying to measure a signal coming from outside the Earth's atmosphere with the receiver on the ground. And what you can see is that the attenuation in this wavelength regime from 300 to 3,000 gigahertz is way up there in the 100 dB range for just going through the atmosphere from ground to sky. And so if you're interested in doing anything in measuring molecular signals from star systems or from other planets or from other galaxies even, you're going to have to put your receivers above the Earth's atmosphere because, as I mentioned, oxygen and water really absorb pretty much everything coming through. And so that is why NASA, ESA, JAXA, they're all interested in terahertz as a driver for satellite observations. And so you have to get above the atmosphere in order to measure these very important molecular signatures that really help you understand what's going on in outer space. So for all of my professional career, we focused on trying to get above the atmosphere in order to measure these signatures. We've used balloons that go up to 100,000 feet, 30 kilometers or so. We've put receivers on airborne platforms like the Kuiper Observatory and now the new SOFIA Astrophysical Observatory. We've had Earth orbiters and planetary sounders that have carried radiometers for doing some of these spectral line measurements above the Earth's atmosphere. And we've used this technology for sensing both atmospheric effects on our own planet up in the stratosphere, measuring things like ozone, water vapor, and other pollutants and chemical constituents that drive processes on the Earth, as well as processes in outer space. So basically, you've got to get above the atmosphere in order to make these measurements, and that means that these are quite expensive systems. As soon as you talk about putting something on an aircraft, a balloon, or even in space, you're talking about many millions of dollars for a receiver, and so the science yield better be very, very strong. Otherwise, you're not going to spend the resources to go that extra mile and really put this very expensive and unique technology on a platform. So for astrophysics, I like to use this quite old chart from Tom Phillips at Caltech, which sort of gives you the justification for why this particular frequency range is so important for astrophysics observations. It's a chart that shows radiance on the vertical axis versus frequency on the horizontal axis, and it shows the spectrum of interstellar dust, 30 Kelvin blackbody curve on the left side in dark black, the 2.7 Kelvin cosmic background curve at the lower left, and then the dust and heavy molecule emission lines that you see superimposed as little hairs sticking up all across the spectral region between 2 millimeters and 100 microns. And I guess the thing to realize here, and the justification and driver for astrophysics purposes, is that the peak black body curves that you're interested in measuring and a lot of the spectral lines that you're interested in measuring that are useful for determining things like gas and dust chemistry, cosmic background physics, or constituents of galaxies and stellar dust, fall in this regime, which we affectionately call terahertz these days. and peak in the region around 200 microns or so. You can see the large carbon-2 line at the very top, which peaks at around 200 microns and is very important for a lot of astrophysics work. So terahertz turns out to be really the principal region for doing line and continuum radiation measurements, and as we mentioned before, it's this sort of temperature range between a few Kelvin and 100 Kelvin or so that really is targeted. And I just put two nice sort of contrasting images that Chris Walker, an astronomer at University of Arizona, sent me recently to sort of illustrate the difference between what you get in the optical regime and in the terahertz regime. The upper right curve of the Horsehead Nebula there shows you the traditional optical image that we're all familiar with if you have any background in astronomy, and the curve or the chart right below at 345 gigahertz just shows you that in this frequency range, in the terahertz range, we're actually measuring the dust itself and not the glow from the stars that are sort of reflecting off the dust that you get in the optical image. So you really can analyze the gas and dust regions very, very well using this spectral regime. So very important if you're interested in understanding what's out there around star systems, spiral arms of the galaxy, and in the cooler regions of interstellar space. And we can identify all those little spectral lines that show up on the curve. Okay, if we go now to galaxies, it turns out that terahertz again becomes a very useful probe for measuring older galaxies or the early universe. So it's very essential for cosmological studies. And the curve on the left in this view graph, which again shows radiance versus wavelength from Bill Langer at JPL, really highlights this. A young galaxy, like shown in the blue curve, has a peak radiance in the optical regime around 1 micron, as you can see from the curve. But as galaxies age, or as we go back further and further in time and see greater and greater redshifts, the energy from those early galaxies really peaks in this frequency range around 100 microns. So if we're interested in probing the very earliest ages of the universe, we really have to work in this frequency range out in the terahertz regime. And a nice little calculation based on the curve on the right, the graph on the right, which shows the radiance versus wavelength from our own Milky Way galaxy. If you look up at the night sky and you're in a nice place with no lights and no atmosphere between you and the stars, that is sort of absorbing the radiance from the optical sky, you can see a beautiful picture of the Milky Way, the center of the galaxy, and you can see from the curve that you get a very, very strong intensity occurring in the optical regime at sort of a micron wavelength. But what you may not realize is that if you go out into the infrared and you go out to 100 microns or so, there is almost 50% of the luminosity from our own Milky Way galaxy occurs in this terahertz regime, dominated by this carbon plus line at 1.9 terahertz. And so that translates into about 98% of the photons being released in this far infrared region. So again, if you're an astronomer and you're not looking out in the terahertz regime at what we're getting from intergalactic and interstellar sources, then you're missing 98% of the energy that's out there. So again, very important for doing any kind of astrophysical observations. So again, just to follow up and to highlight some of the missions that we were fortunate enough to work on for astrophysics, the latest mission carrying terahertz receivers was the Herschel Space Telescope. It was launched in 2009 by the European Space Agency. And just to give you an idea of how much investment has gone into this frequency regime through the space missions, this particular instrument cost more than $1.5 billion. It was under development for more than 20 years. Literally hundreds of engineers and astronomers around the globe have worked on it. It's been a major, major science success and has really contributed just thousands of papers now in sort of galactic structure, cosmology, stellar evolution, and nature of the universe. So just a tremendous achievement, and there have been actually 11 other missions with terahertz sensors that have flown since 1978. So a lot of emphasis, a lot of money has gone into this particular application for terahertz. And you might say it's really the killer application for this frequency regime. And I mentioned very briefly, you can also use this technology to look at the Earth, and there have been 4 missions to date, 2 from JPL that have carried terahertz sensors to look at the stratosphere and to measure things like ozone, water vapor, sulfur dioxide, fluorine monoxide, etc., for understanding things like global warming, atmospheric pollution, ozone depletion. And this has been a very, very strong priority since the 90s, and of course will continue to be a very strong priority as we go forward in trying to really understand climate change and how all of the different processes that happen on a global scale affect the Earth's atmosphere, and especially ozone, which of course was basically mapped and dealt with because of the space science that was done in this frequency range, looking at the chlorine monoxide relationship and gobbling up of ozone through that chemical process. And finally, there's been one mission that has used terahertz receivers for planet or comet. In this case, was also a European Space Agency mission on Rosetta orbiter. We had an instrument called Miro, which was launched in 2004 and rendezvoused with comet Churyumov-Gerasimenko in 2014. And it measured carbon monoxide, water, ammonia, and methanol as it outgassed from the comet as it approached the sun. And a lot of, again, interesting information about comet chemistry as well as evolution and formation of comets can come out of these kinds of measurements. So I guess I just want to emphasize that even if there were no other applications for this field, this particular suite of planet and Earth and astrophysics missions and instruments is something that really justifies the investment in the field to date. Has been, I think, a very, very strong motivator for terahertz technology. Okay, so with that in mind, now let's look at something a little closer to home and talk a little bit about the approaches and what we might be able to do with terahertz if we're not interested in astrophysics. So I would sort of classify the approaches to doing terahertz instrumentation with three major thrusts. The first is what I just talked about mostly, which is the traditional radio frequency technique where we take microwave transmission lines, waveguides, antennas, sources, and detector technology, and we translate it up in frequency into the terahertz regime in order to capture the spectral content that exists only in that wavelength band. And a lot of this sort of technology investment has really come from the astrophysics community. It was pioneered basically in the 70s as sources became available in this wavelength range and has undergone continuous development since then. And so you can sort of take the Radiation Lab series from the 1950s and 60s and apply most of that analysis and come up with the same technology and techniques that were used in the radio wave bands and apply them in this higher frequency regime to do very similar things. And there's been a bit of improvement, but it hasn't been quite as dramatic as you might think, and most of those earlier techniques work quite well in the higher frequency regime. Of course, solid-state devices are rolling off in performance, and it's very difficult to make integrated circuits at these higher frequencies. But there have been major strides in that department, and things are actually not so bad these days in terms of custom components. Now, there's another technique that people also used back in the 1970s, late 70s, early 80s, which involved generating terahertz signals using optical sources and using an intervening crystal or a photomixer to do optical rectification. But that sort of came about when narrowband sources like lasers were able to be applied to nonlinear crystals, and down converting from the optical into the terahertz regime became possible with pretty narrow line width. And although the efficiency was very poor, so we're talking maybe 10 to the minus 4 or 10 to the minus 5 conversion efficiency, optical sources are quite strong, and so you're able to generate microwatts of power in this frequency range in the terahertz band by doing the optical conversion techniques. And then in the late 90s and more recently still, direct oscillation using quantum cascade lasers, engineered bandgap materials came online, and now you can generate milliwatts of power in the terahertz frequency range with these narrowband sources. And then finally, the third technique is to essentially use Fourier transform spectroscopy, or to generate broad band terahertz energy through time domain technique using a fast femtosecond laser and the same kind of frequency conversion techniques that optics people used in the 1980s to generate very wide signals with not too bad power content, but sort of microwatt levels of power throughout the terahertz range by making sure you have a laser that has a pulse width of only a few femtoseconds, so that you get very broad terahertz signal response from the Fourier transform. And you can build a spectrometer, which is essentially the temporal equivalent of a spatial Fourier transform spectrometer using optical time domain pulse technique. And that's really opened up a lot of applications for terahertz. So just to highlight that, here's a very old slide just giving you a block diagram of how this works. You take a femtosecond laser, beam split it, and send one part of the optical signal through a delay line, impinge that optical beam on a terahertz detector or a detector that converts the optical energy into a terahertz modulation, and send the other side of the beam from the optical laser into a terahertz generator, an optical switch or a photoconductive device. And then by scanning the optical delay line, you can build up an interferogram, which you can see on the chart in the middle. And that interferogram can be Fourier transformed to give you frequency content that covers the full terahertz band. And once you have that terahertz broadband pulse, you can use that to do spectroscopy and do it over a very wide bandwidth. So that time domain approach has really expanded the terahertz community significantly. Many optical folks who were working on lasers came into the community in the late 90s using these fast laser techniques to do terahertz imaging and spectroscopy for all kinds of applications that were proposed in terms of spectroscopy and material identification. People tried to do bio materials, pharmaceuticals, and environmental applications and monitoring. In fact, I'll refer you later on to a copy of our terahertz transactions that really has a bunch of background articles on applications that covers this quite well in the November issue that was just released a few weeks ago. So you can see I put a reference here for that, but if you get that issue of the Terahertz Journal, you'll find all kinds of articles on applications time domain. And I said non-destructive evaluation has always been a niche for terahertz, but with the advent of time domain spectroscopy and very broad terahertz spectral techniques, which also give you time of flight and thickness variation, as well as amplitude and phase of dielectric constant. You can do things like measuring the thickness and dryness of paint, pill coating integrity, cracks and voids in carbon fiber materials, which have been used for aircraft as well as wind turbine blades, water content in materials. People have tried to do measurements of rust damage under paints. Even people in the art world have used this for trying to look at actually dating the paint by certain paints by their lead content, for example, and also for looking under paint at properties of canvas or other layers of paint, or through pottery, which is somewhat transparent to this wavelength range for art historical purposes. And finally, thickness measurements of dielectrics, etc. So all of these are quite niche and depend on whether or not you really need something expensive and fairly slow, but you have no other choice because you can't do this with other frequencies. Terahertz can sometimes play a useful role. And then finally, in ultrafast chemistry and nonlinear optoelectronics, looking at charge distribution, molecular motion, especially water hydration shells, sometimes conformational state changes of certain molecules, or dynamics of nanostructures or near-field microscopy can all be done with ultra-fast lasers and this broadband time domain technique. So again, none of these are very mainstream, but they're all niche applications that may find a home in the future. So if you have an application, you haven't really got any other way to measure the change in water content on a small scale, or some other chemical change that maybe isn't available in the infrared, then you might try terahertz for that. But I just want to point out the difference between terahertz spectroscopy on lightweight gases which is what astrophysicists are interested in, and people doing spectroscopy on liquids and solids or gases at atmospheric pressure, the fingerprinting is far, far, far superior if you can do gas under low pressure, as demonstrated on this chart. You're looking at nitrous oxide, one single line of many hundreds of spectral lines that occur in this frequency regime at 627.75 gigahertz for this example. And you can see the magnitude and phase of the absorption signature for this gas under low pressure. And if I switch over here to one of the better techniques for measuring spectral lines in liquids and solids, this one being an example of a mesh technique that was used to demonstrate the spectral content for hemoglobin and D-glucose dextrose in a powder form. You can see the scale at the bottom here goes over a 2 terahertz frequency range, and yes, there are specific signatures that you can see for both hemoglobin and glucose, but those signatures are extremely broad compared to the equivalent gas signature from nitrogen, and also the signal to noise is very, very reduced compared to the gas signature that we can get. In fact, I've drawn the line much, much thicker than it actually should be. You wouldn't be able to even distinguish the N2O signature on the scale, on the X scale of that graph that I've shown. So if you're trying to identify species with terahertz, it's not nearly as good a signaturing or fingerprinting technique as you get in the infrared, for example, or even in the optical regime, unless it's a lightweight gas under low pressure and or low temperature. Okay, so now let's talk about some really big potential applications. And I guess the two that stand out the most that people talk about these days are communications and imaging. And we'll talk a lot about imaging. I'll talk only briefly about communications, because communications really is not at this point a terahertz application so much as a millimeter wave application. It is true that if you can go above 100 gigahertz, you can get a lot of bandwidth allocated to your communication system that is not taken up by the many other communications devices that exist in the world. But also the atmosphere becomes very, very absorptive. So you're not going to be able to use this really above 300 gigahertz with any long distance type of communications. But for point-to-point links or some even chip-to-chip type systems, or maybe even network backplanes, there may be a use for very high-speed COM type circuitry that can use terahertz devices. And I'll point out just a few of the things that people have been working on and pushing in this field. Sorry, this graph is a little bit busy, but basically because of the advent of these nice unitraveling carrier photodiode transceivers that people have been working on, largely in Japan, you can now get signal transceivers all the way up to 600 or even a little bit above 600 gigahertz direct from optical to RF. And in 2008, NTT actually demonstrated an HDTV coupling over about a kilometer distance, I believe, that was actually used at the Beijing Olympics and has since demonstrated 10 gigabit per second over almost 6 kilometers for direct communication system. There have been people who have been working hard at much higher bit rate systems. 100 gigabit per second, I think, is probably the record, as far as I know, for a COM system at 237 gigahertz over a 20-meter distance. That was demonstrated around 2013 by a group in Germany. And 720 gigahertz, 1.5 gigabit per second was demonstrated recently at Osaka University. So very high data bit rates are possible. Again, we're talking really millimeter, not terahertz for this application. I think for really useful instrumentation, but I think there is some potential here. And on top of UTC photodiodes, there's also been a very large investment in traditional indium phosphide hemp technology coming up from the millimeter into the terahertz band, notably in the U.S. by DARPA, that has invested over $50 million in this technology and has had tremendous success in getting now low noise mimic circuits at 1 terahertz, power amplifiers at 850 gigahertz, and they've invested both in hemp and HBT technology, notably at Northrop Grumman and Teledyne in California, but other places as well. And also tube sources have now been demonstrated above a terahertz, again, from the same program. So a lot of advancement in more traditional solid-state technology that presumably can be applied in the communications application if it turns out to be very, very necessary and useful. And there have also been a lot of advances in detector technology, I guess notably the Michael Shore Diakonov CMOS silicon-based plasmon detectors, which have very low NEP now and have been demonstrated in large arrays up to a terahertz for doing very sensitive detection and imaging. And I'll just mention that the US FCC has really yet to do any band allocation above 275 gigahertz, although they're taking comments now and thinking about it. You can contact Mike Marcus. I've left a little reference for him, who's used to be at the FCC and is very interested in this idea of allocating band capabilities in the submillimeter regime. Europe and Asia are already working on regulations up to 1,000 gigahertz. So I guess the real draw here is that if you need bandwidth and you go above 100 gigahertz, there's plenty to be had, and you can really do some nice high data rate types of comm if you need to do that over reasonable distances. And there are basically 3 or 4 atmospheric windows you can work at, and I'll show you those in a... Wow, I am really running out of time, aren't I? Okay.
I'm afraid so. Peter, can I interrupt you right now, or is there one more point you'd like to make?
Well, let me just mention a few other quick things here, because I really haven't gotten into it nearly as much as I'd like to, and I'll skip the bio work. But let's talk a little about imaging, because I think that's important. And if can I run over about 5 or 10 minutes? What do you think?
I think we have to do a hard stop. A lot of our listeners need to wrap up after the hour that they've set aside. Maybe we can do another session some other time.
Okay. All right. Well, let me just say that the other big topic people tend to look at when they're doing terahertz is imaging, but you really have to be very careful because the absorption in things like water and biomaterials is very, very large, so it's very difficult to do much more than minimal penetration through objects, but you can come up with techniques that work. I'm going to have to go quite quickly, so I'm just going to go to the a few slides here that show you how you get away with this. If you work in an atmospheric window, like I show here on this slide at 670 gigahertz, you can do some things with active imaging and radar reconstruction that allow you to get object recognition with much better identification than you can do either with passive or with active imaging without the third dimension radar gives you, which is depth. And you can do this by essentially doing a chirped, I'll have to skip over to this. You'll have to look at these on your own, and maybe during the questions, but by doing an FMCW type of chirped frequency pulse and using the return down-converted signal in a heterodyne system to give you range information and bandwidth of the chirp to give you range resolution, you can make a three-dimensional reconstruction of an object and essentially be able to measure something that looks very unidentifiable in just a straight image that involves intensity only, as you see in C on this view graph. But by using range binning, you can actually hone in on the object itself, the first reflection, as you see in D, or the reflection off the last item in the range bin in F, to actually bring out an object using a radar approach. And I think I am going to really have to end it without giving you too much more information live, and maybe we'll have to schedule another part 2 of this to go through the other half of the view graphs. But let me, I guess, skip all the way to the conclusions here and end it for you and give you some questions you can ask. Let's see, can I that over? Okay, skipping over the other 50% of the information. Sorry about that. Let's just sum up so most of you can go and do other things. So terahertz really began with the radio astronomy, plasma science, and physical chemistry community in the 70s. In the late 80s, early 90s, the optics community came in and have, with both these communities together, have provided a sort of variety of techniques that can be used to do spectroscopy, imaging. You'll see if you go through the view graphs, other things that you can do with terahertz that I didn't get a chance to mention. With technology that is still evolving, but has a lot of potential, I think. Since most of the techniques that people have used in the past really come from very solid, solid-state circuit technologies that have come up from the microwave regime, there's a lot of already components and devices available that can be used, but the real commercial application for expanding these into very inexpensive off-the-shelf components has yet to really materialize. And I didn't get a chance to go through it, but although imaging is a very well-hyped technique, you have to be very, very careful how you do it. And you really can't essentially rely on the optical equivalent of high resolution, high contrast to be able to identify objects. You have to use more subtle techniques like radars and three-dimensional reconstruction using time domain in order to identify objects that essentially exist under lower contrast and high speckle. And we didn't get to talk at all about the millimeter effects on the body, but I've got a whole slew of slides on those you might be interested in looking through. And of course, you can either communicate with me directly, look at the references, or maybe we can schedule another one of these where I can go through that second half of the terahertz slides and more. So I guess I better end it here, and next time I better talk a lot faster. So if there are any questions, I'll be happy to entertain them. And again, I apologize for not getting to the majority of the slides. Okay.
Thank you very much, Peter. I'm afraid we don't actually have time for questions at this point. I personally would like to see another presentation, and I'd like to let our listeners know that while we do have a number of very good questions in the queue, we will forward those to Peter and force him to answer those offline. And I'm only joking about the forcing part, Peter.
I'll be happy to do so, Doug.
Okay. As we said earlier, the session will be archived, and all registrants will get an email reminder with a URL when it goes up. The attention during this webcast has been extraordinary, as reflected in the fact that everybody was with us for the whole time. That's unusual. So once again, I'd like to thank Peter Siegel for an illuminating hour. Our thanks, too, to our sponsor, National Instruments, and special thanks to our audience for joining us today. We do hope you found today's event valuable and that you return for future IEEE Microwave Theory and Technique Society webcasts. Have a good day.